This is the Chem 1 lecture for oxidation states and redox reactions. So the first part of today's lesson, we're going to talk about how do we assign oxidation numbers, and they look really similar to charges back like in Unit 8 where we had +1, +2, +3, etc. However, oxidation states represent the charge that an atom would have if the electrons were transferred completely. And so mainly we're going to be looking at covalent compounds and even into polyatomic ions, but then going specifically to the oxidation number of nitrogen and the oxidation number of oxygen. So this will not always match those periodic table numbers that y'all had memorized in Unit 8. And so we're going to teach you a very step-by-step process of how to assign oxidation states. And it's really important to remember that an oxidation number or state is for one individual atom. And so, like I just mentioned earlier, it's going to be for specifically nitrogen and oxygen, not the whole group anymore. So similar in Unit 8, when y'all were having to solve for those multivalent or unpredictable elements, we would equal things to 0. Sulfate was -2, therefore copper must have been a +2. That's going to be similar in that oxidation states must add up to the charge of the molecule. A lot of molecules do have a charge of 0. So if you don't see any charge, then you can assume the molecule is neutral. And then any element in its elemental state will also be an oxidation number of 0. So the only difference is when you're working with a polyatomic, for example, ammonium, because it has a +1 charge, all of the individual oxidation numbers would have to equal +1 instead of kind of the typical 0. When you're working with an ion, it is going to be equal to the charge of that molecule. Okay, so let's talk about how we're going to assign oxidation numbers. And so on your notes, you have this rule boxed in. I would definitely highlight it, star it. These are things you want to memorize. And if you do enough practice, you'll just kind of naturally know the rules. So, and then the key thing is you have to use the rules in order. So something that always ends up being a little tricky is that sometimes you're going to see sulfur be a -2, but other times you might see a crazy number like +6. And so you'll know which number it's going to be by following the rules in order. And so you'll assign oxidation states until there's only one element in the molecule left, and that will be your unknown. And so once we practice, it'll make a little more sense, but if sulfur is your last element, it's going to be unknown. It's not always going to be -2. So remember, oxidation states are different than charges like the ones we were using in Unit 8. Okay, so we're going to go through, I think there's 5 rules, and so we're going to go rule at a time. So rule number 1 in order is if you have a metal, we would call it Katzenagel back in Unit 8, that kind of diagonal, you would assign those elements first. They're going to get preference in assigning oxidation numbers, and the charge that you did see in Unit 8, silver's +1, zinc and cadmium are +2, and aluminum is +3. Rule number 2, so if there's not Katzenagel or there's more than one element, you move to rule number 2. Any alkali metal would be assigned a +1 charge. Any alkaline earth metal would be assigned an oxidation number of +2. Rule number 3, if you still have more elements to label, if you have a hydrogen, then we're going to assign the oxidation number of +1. Rule number 4, if there's an oxygen present, it's going to be assigned -2. And rule number 5, if a halogen is present, you're going to assign it an oxidation state of -1. So the halogens, like in Unit 8, always have that -1 charge. And our last rule, there were 6 rules, is sulfur. If sulfur is present, assign an oxidation state of -2. So here's a recap of all 6 rules. First, look to see if you have any Katzenagels. They would get preference on their charge. Then look for alkaline earth metals, then hydrogen, then oxygen, then halogens, then sulfur. And then once again, this will make a little more sense when we practice, but this little bubble is really helpful. Use the rules until there is only one element left in the compound. Even if it's on the list, your last element will always be unknown. Okay, so let's practice on number 1, sulfuric acid. So let's go rules. Number 1, do you see any Katzenagel? Nope. Rule number 2, do you see any alkali or alkaline earth metals? Nope. Rule number 3, is there a hydrogen? Yes. Hydrogen, we're going to assign it to be a +1 charge. Okay, rule number 4, I think it was oxygen, is it a -2? And that is true. And so then even though sulfur is listed on this, like if we were to keep going on our rules, you assign everything until there is one unknown charge. So sulfur is going to be our unknown charge. Okay, so that looks like a little messy. So then once you've assigned your oxidation numbers, you have to kind of distribute, like you have to take into account that there's 2 hydrogens. So I write on top and then I bring it down. So 1 times 2 is a +2, and I'm going to come over here. X, and there's only 1 sulfur, so that's 2 plus X. And then each oxygen is a -2 charge, but there's 4 of them, so that's -8. And I'm going to equal this to 0. Now, why did I equal it to 0? Because H2SO4 is a neutral molecule. First, when we get to number 2, that whole molecule has a charge, and so we would equal it to -1. Okay, so we're going to solve for X. So 2 plus X minus 8 is X minus 6, and then add 6 to each side. So X, our unknown charge, is +6. And X was representing sulfur, so the oxidation charge of sulfur is a +6. Now, we need to go back and fill hydrogen and oxygen. Remember, this is for, the oxidation number is individual. It's not a total. So we go to that top part. So hydrogen has an oxidation state of +1, and oxygen has an oxidation state of -2. We a lot of times see I'll put totals in there, like -6. We use that to solve for X, but ultimately it's the individual charge that we want as our final answer. Okay, so let's try number 2. So to assign oxidation numbers, you start with your rules in order. So number 1, do we have any Katzenagels? Nope. Rule number 2, do we have any alkaline or alkaline earth metals? Rule number 3, do we have a hydrogen? Yes. So we're going to assign hydrogen an oxidation number of +1, and then oxygen is going to be our unknown, which might feel strange, but that's going to be our X. So while I'm thinking about it, we know hydrogen's individual charge is +1. So then we'll apply down. There's only 1 oxygen, so it's X. There's only 1 hydrogen, so it's +1. And then where this looks different is that because there's an overall charge, my overall molecule has to equal that charge. So X plus what equals -1. So opposite, if you minus, X must equal -2. So in this case, oxygen does have an oxidation state of -2. All right, let's try example number 3, hydrogen peroxide. So following the rules, the first rule we come across is hydrogen. We'll get a +1. Oxygen's going to be our unknown. I'm already going to fill in hydrogens over there. Make sure you apply the ratio or the charge, apply down. So there's 2 hydrogens, so it's going to carry a charge of 2 plus, there's 2 unknowns, so that's 2x. And then the whole thing can equal 0 because it's a neutral molecule, there's no charge. So then let's carry this over, 2x minus 2, am I on the right? Wait, 2x equals -2. And then divide by 2. So x is -1. And so we liked putting these examples back to back because with oxidation numbers, those oxidation numbers can change based on who they're bonded with. So sometimes oxygen is that kind of familiar -2 charge, but there's other times oxygen might carry that -1 charge. So that's why going through the rules in order is so important. Okay, example number 4 is a little different because we have a polyatomic and there's multiples of that polyatomic. So my preference is to rewrite this formula with everything distributed. Okay, so we will have still 1 aluminum, but we'll have 3 nitrogens and 9 oxygens. And then start going through the rules in order. Rule number 1, is there aluminum or Katzenagel? Yes. So I'm going to apply a +3 charge to aluminum. Okay, we have rule number 2, there's no alkali metals. Rule number 3, no hydrogens. Okay, we have an oxygen, so that's going to carry a -2. That means nitrogen is our unknown. And so remember, oxidation numbers is for the individual charge, not total. So aluminum is going to be +3, oxygen is going to be -2, and we are solving for nitrogen. To solve for nitrogen, this is where I just kind of say drop it down. So it's going to be 3 plus 3x, so I just multiplied down, and there's 3 of them, and then 9 times -2 is -18, and the whole thing equals 0, because this was a neutral molecule. So then just combine like terms, so 3x minus 15, right, combining the 3 and the 18, equals 0, carry over 15, divide by 3, X is a +5 charge. Okay, let's try example number 5, a carbonate ion. So we're going to assign oxidation numbers using our rules. Looks like our first rule we come across is oxygen, carrying a -2 oxidation state. Carbon is going to be our unknown. And so if I multiply down, we have X, and then -2, and there's 3 of them, so that's -6, and then this molecule has an overall charge of -2. So then we can add 6 to both sides. X is equal to a +4. So the oxidation number of carbon in this molecule is +4. And our last example is so simple it's almost hard. So it's sulfur with 8, and because sulfur is not in a bond with anything but itself, it's considered in its elemental state. Therefore, it hasn't given or taken any electrons, and so sulfur's current oxidation number is 0. So anytime there's just an element, it could be diatomic, it could not be a diatomic. In this case, there was 8 sulfurs. The overall oxidation number is a 0. Magnesium. So if they're not in a compound, which requires 2 or more elements chemically bound, then the oxidation state is 0. So now we're going to do the same thing, but in an entire chemical reaction. So it's going to be the same process. You have to tackle one molecule or one element at a time, but we're going to assign oxidation numbers to all of the molecules. So kind of my preference is I always just look for the elements because that's really simple. They're just always going to be 0. No electrons have been given or taken, so the charge is 0. So it looks like oxygens are only elements. So before the reaction, it had an oxidation state of 0. Let's take on this molecule CH4. So following our rules, hydrogen would be the rule we come across first. Our unknown is carbon. So that's X plus 4, because I multiply down, equals 0. And so X must be, in this case, a -4. So carbon's oxidation number is a -4, and hydrogen is a +1. All right, on the other side, oxygen would be -2, our unknown's carbon, X minus 4 equals 0. So carbon's oxidation state is a +4 on the product side. And then hydrogen becomes first. Remember, you have to follow the rules in order. So that means oxygens are unknown. So then if you multiply down, that's 2 plus X equals 0. And so X must be a -2 charge. And hydrogen was that +1. And then it says, circle the elements that have changed oxidation number, so before and after the reaction. So let's just look at one element at a time. So carbon was -4 before, it changed after the reaction. Hydrogen was +1, hydrogen still +1 before and after. Oxygen was 0, and then it changed to a -2 charge. And so we're going to kind of switch gears. So the first half of this lesson was how to assign oxidation numbers. And then the second half is what's the point? Why do we care about these oxidation numbers? And we have specific names for when we see charges become more positive and when we see charges become, or oxidation numbers become more negative in a reaction.